Hello, I am Sir CJ, and this is the 42nd edition of Physics 9. In this edition, we are going to be tackling the following parts. The first and the second, as well as the third part, are actually coming from the same division of the 7E based self learning module in Science 9, which I wrote for my master's degree. The first one is a discussion about the first law of thermodynamics. The second one is a discussion about thermal efficiency. And then the last part is a problem solving activity. It is a guided problem solving on thermal efficiency. This session is actually one of those sessions where we have so many learning competencies. And the first among them is for you to be capable of constructing a model to demonstrate that heat can do work. And then the second learning competency is for you to be capable of inferring that heat transfer can be used to do work and that work involves the release of heat. And then the last learning competency for this session is for you to be capable of explaining why machines are never 100% efficient. So we have that already over here. For you to actually, this is lifted from the book which I wrote. Particularly, you will see these parts on the 11th to the 13th pages of the 23rd book of the fourth unit. Ayan. Okay, so I hope that you are now ready. Let's begin. For the first part, for the discussion about the first law of thermodynamics, you have seen as actually, I am assuming, how thermal energy can cause things to move. In the previous activity, yung coil of paper, it was moving not because it was being blown by the wind. Well, it can move actually by being blown by the wind, pero it's kind of movement, the kind of movement it did in that particular instance was actually caused by thermal energy that is coming from the source. This is an evidence of the transformation of thermal energy into mechanical energy since ayun nga, from the heat from the thermal energy the source has, nagiging mechanical energy siya, and this was made possible by the spin by the actual parang coil of paper. Yung coil of paper has the ability to turn that thermal energy into mechanical energy in the same way that ang mga turbines, they can turn thermal energy into mechanical energy, which is actually this actually is the main theme of a branch of science called thermodynamics. Now, as a branch of science, thermodynamics has certain laws. The first law of thermodynamics states that the total increase in the thermal energy of a system is equal to the total amount of work done on it and the heat added to it. Ang sabi dito is yung kung gusto nating malaman kung gaano karaming thermal energy ang na-release ng system, we have to compute for the total amount of work na nagawa ng system and as well as the heat that was added to it, kung gaano siya kainit. Okay, so halimbawa, ang isang bagay ay gumalaw or nag-move from one place to another and then uminit siya, then we can say that we can use those two evidences, yung work na nagawa niya at saka yung init na nadagdag sa kanya, for us to be capable of computing the total increase in the thermal energy of that system. To illustrate this better, let us take some heat engines, for example. The earliest known heat engine is right here sa illustration na to. It is called an aeolipile. Okay, nabubulol pa rin ako when I say this. Aeolipile. This was invented by Hero of Alexandria in 200 BC, and it is composed of a sphere tank, so ito, that contains water with two tubular spouts where the steam can escape. Dun lalabas yung mismong steam. Now, the spherical water tank is heated, naiinit siya, causing the water inside to boil, forming the steam. So as you can see here, itong parang whitish na to, tsaka itong whitish na nandito, these are actually steam na nanggagaling dun sa loob ng aioli pile. The steam will be rushing out of these tubular spouts that are actually bent 90 degrees, ayan, causing the whole engine to rotate. So dahil ganyan yung orientation nila, ito pag ganun yung steam na lalabas, ito naman pag ganun yung steam paglabas. So it's gonna be expected to actually rotate clockwise. I am sorry ha, maybe you're hearing a lot of no dog noises at the back in the background, pero I'm gonna be attempting to remove that sound as much as possible in the editing. But I hope that we made this yung aioli pile as clearly as possible. Ayan, naririnig nyo sila. Hindi sa amin aso yan. Okay. Now, with the input of thermal energy dun sa aioli pile kanina, the engine was creating an output of mechanical energy. So, let's go back. Yung pag-init nito, yung pagpapainit nito, ibig sabihin we are actually adding thermal energy to it. Tapos naman, yung kanyang nagiging product, yung kanyang nagiging reaction to that is the production of a mechanical energy. At dahil yun, sa pagkaka-design din ng engine na to, na umiikot siya, kumbaga pwede siya mag-rotate. Okay, so it is capable of creating turning it into mechanical energy. So, question lang, do you think yung aioli pile kanina, okay, balik ko, iikot ba yan kung hindi natin pinainit yung tubig sa loob? Okay, I think naman you'll agree na hindi yan iikot. This concept, yung concept ng aioli pile, was later on applied to some other practical uses. So, hindi lang siya para sa mga laruan tulad ng aioli pile. It was actually, kumbaga, used and applied in the concept of the first engines na ginagamit para sa mga tren, sa mga trains. Yung heat source has a certain amount of thermal energy. So, in this train, we can say na meron siyang heat source, okay? And that source is kumbaga, pinanggagalingan, obviously, ng thermal energy or TH, or the temperature of the heat source. So, again, the thermal energy here comes from the heat source, and we can say that that is TH. Now, part of that thermal energy of the heat source, or HH, yung part lang niya, hindi yung buong thermal energy ha, part lang nun, or HH, or the heat that gets transferred to the heat engine, is, transferred to the heat engine. Now, with the input of HH, yung nadagdag dun sa heat engine, the heat engine is going to do work. Okay. Now, you see this illustration, yung heat source has TH. It's gonna apply thermal energy, add thermal energy to the heat engine, and then the heat engine is gonna do work. And then some of the heat or some of the thermal energy is gonna be added or gonna be routed to the heat sink. Okay, so at this area, dito nangyayari yung pag-a-add ng heat. Dito naman sa area na to, nangyayari yung pag-waste ng heat, itong banda dito. Some of the thermal energy from the heat engine, left from the production of work, or HC, or the heat that is left from the production of work and is being transferred to the heat sink, is released towards the heat sink. As I explained kanina, the heat sink has its own temperature. So that temperature is labeled as TC, or the temperature of the heat sink. Sa bawat pagtatransform, saan ba nangyayari yung transformation? Siyempre, dito sa heat engine. It's gonna transform it into kind of work, okay? Through mechanical energy, in the form of mechanical energy. Now, in every transformation by the heat engine, the whole amount of thermal energy input does not get to be converted into work by the heat engine. Let me emphasize that. Yung buong amount ng thermal energy na nanggaling sa heat source, hindi yun necessarily lahat nagiging converted into work. Hindi lahat, no? some of the input energy, thermal energy, is just wasted and gets dissipated, or yun nga, nasasayang lang siya or disintegrated and wasted into the heat sink. So, limbawa, sabihin na lang natin kung i-quantify natin yan, meron kang 100 na thermal energy from the heat source, sabihin na lang natin na yung 75 nagagamit para makagawa ng work, tapos yung natitirang 25, nasasayang lang actually, napupunta lang dito sa heat sink. Okay. Now, may mga, syempre ganito, no? Kung halimbawa, may heat engine ang isang tren, syempre gusto natin na yung amount of thermal energy na kumbaga in-input natin diyan, na kumbaga ginawa natin para mag-work ang isang tren. Gusto natin lahat ng thermal energy na 'yon magamit, 'di ba? Kumbaga para mas malayo ang marating ng tren. Ang gastos kaya ng susunog, 'di ba, ng sabihin natin ng coal, pagsusunog halimbawa o kaya ng diesel, 'di ba? Ang gastos kaya noon, tapos nakaproduce ka ng 100 thermal energy, tapos 'di ba, like 75 lang yung magagamit. Tapos 25 sayang lang siya, hindi man siya magagamit talaga, right? Okay, so even though that was a very primitive kind of train, ang application nun hanggang ngayon actually meron pa rin siya, kasi I know napakatagal na nung pinakaunang engine for the train na gumagamit ng ganong klaseng application of water, gagawing steam. Ngayon alam naman natin na gas na yung ginagamit natin, no? Pero we're actually having the same kind of application. Heat engine pa rin yun. Yung mga ginagamit natin madalas sa mga machines natin ngayon. And our machines are still kumbaga incapable of turning the heat input, the thermal energy input, and maximizing it into turning it into work, tapos walang gaanong kumbaga wasted heat na napoproduce. Kumbaga, siguro as time passes by, yung 75 na nagagamit for work, nagiging 76, di ba? Kaya, maybe even 85. Pero not all of it talaga is being maximized, at hindi lahat, kumbaga, nagagamit for work. Meron at meron pa rin talagang natitira. Now, that concept is actually called thermal efficiency. The efficiency of a heat engine, relies on how much of the input thermal energy it can transform into work and how less heat it actually wastes. Again, ang sinasabi lang natin dito, yung efficiency ng isang heat engine is dependent, or madedescribe natin yun kung titingnan natin yung input na thermal energy at yung output. Okay, so kung halimbawa yung input mo na thermal energy is 100, tapos yung output mo is also 100, then we can say na yung heat engine is 100% efficient, and that is its thermal efficiency. The thermal efficiency of a heat engine is yung ratio of the output of work of the heat engine and the amount of input energy. So its formula is as follows. So thermal efficiency is equal to output work divided by the input energy multiplied by 100. Okay, so in symbols, yung output work is symbolized as W, and then the input energy is symbolized as HH. And remember that this is the thermal energy that came from the heat source, okay, that went to the heat engine, and you multiply that by 100. The resulting factor will be a percentage, as it's made obvious over here. We multiply it by 100. It's gonna be a percentage, and it describes the efficiency of the heat engine. So, yung percentage na yun, kung 100% siya, ibig sabihin, that is the efficiency of the heat engine. Now, based on the first law of thermodynamics, the amount of work done in a system kailangan equal siya dun sa amount of change in the thermal energy. Okay, so again, the amount of work done in a system, kung para malaman mo kung gaano karaming work ang ginawa sa system, kunin mo muna yung thermal energy ng system before, okay, na-apply yung work at yung thermal energy ng system after ma-apply ng work tapos get its difference. And you will get work. Ayan. Now, tandaan natin, maalala natin that in the formula before this, meron tayong W rin doon, di ba? It's actually here, a W. Andyan siya. You can remember that. We substitute the formula for work, itong sang to, H sub H minus H sub C. Okay, in the formula, dun sa previous formula kanina, to get the final version of the formula that involves the amount of thermal energy input and wasted energy. Kasi may mga times na yung work hindi naman binibigay. Ang binibigay lang yung H sub H and H sub C. So in that case, yung W gets replaced by them. Okay, so it's gonna be H sub H minus H sub C divided by H sub H, and that's multiplied by 100. Parang nag-iipag-duet yung aso, no? Naririnig niyo pa rin ba? Pero nevertheless, I hope na you are hearing me better than my neighbor's dog, and that you understand kung bakit naging ganito yung ating final na formula. So we actually put together yung thermal efficiency formula na to, atong itong isang to formula for work, and it's now turned as just one formula. Now we will be trying this out in the sample problem. Okay, it's a guided it's a guided problem solving activity for thermal efficiency. Let's see if you already get it correctly. All right, so grab your piece of paper. I think for this, you're gonna be using a 1/2 crosswise sheet of paper, and of course, pen and your calculator. Your problem is as follows. You have to compute for the thermal efficiency of a gasoline heat engine that receives an input of 194.5 joules of thermal energy. So that's the input from a heat source, and it loses 143.3 joules of it to the heat sink in a cycle. So, tingnan nyo to, no? Yung naging input niya is 194.5 joules. Tapos, yung nawala, okay, is 143.3. So, how efficient do you think is this heat engine? All right. For now, I'm gonna be asking you to list down your givens. Make sure na malabel mo sila ng properly, and make sure that you know which formula to use, since in this problem hindi binigay yung work na nagawa ng heat engine. Then we assume that the last version of the formula is what we'll be using. So go ahead and write the givens. Are you done? So your givens must look like this, ha? So H sub H is equal to 194.5 joules, and then H sub C is equal to 143.3 joules. So what do you think are we missing? All right, we're missing thermal efficiency. Okay, so we now proceed to the make sure anyway na you followed more or less this kind of form, kasi this is the fastest way to do it, okay, and the most kumbaga organized way of doing it. Let us now jump to our solution. You have to use the following formula, of course. It's found already dun sa previous parts ng notes ninyo. Okay, so that's a formula. The second thing you'll be doing is substituting the givens. So go ahead and substitute the givens. Are you done? Okay, so the given factors are as follows. So we have here 51.2 joules and 194.5 joules multiplied by 100. All right. So I think that you see as well here na since 51.2 joules na siya, we assume that we immediately took kumbaga the difference between the two. But if you haven't done it like this yet, it's fine. Okay, it's fine. Now, what are you going to do for the last part? Of course, you're going to carry out the operation. Please carry it out. Are you done? All right. So the thermal efficiency of the heat engine in this case is only 26.32%. Did you get the answer correctly? Make sure it has percentage in it, ha. Kailangan meron siyang ganyan. All right. Um, this heat engine is not 100%, if it's actually far from it, no? Halos sumobra lang siya ng konti sa quarter efficiency. It actually means to say that this heat engine was not capable of achieving that. And this one as well, itong statement na to, is actually quite general. It's actually true as well. We're trying to create a machine that is 100% efficient, pero actually hindi sila naging efficient. What do you think is the reason for that? Well, think about this. Um, when a toy car that is battery operated is kumbaga has been running around, is being played for an extended amount of time, then you turn it off, you will know. Okay, kahit hindi mo man nakita na pinaglaruan siya ng kung sino mang may-ari sa kanya, you will know that it was played with by just touching it kasi medyo warm pa siya. Okay, maybe its motor is still quite warm, right? And what do you think is the reason for that? Okay, it has been moving. It has been having mechanical energy. Yung mechanical energy na yon, nagiging possible yon because of the power that it is getting from its batteries, and that allows it to do work, right? To exert force and cover a distance. But at all times, most machines, if not all of them, most engines, if not all of them, are always going to produce thermal energy. Mainit sila, right? Halimbawa, yung mga television natin, after they did work, mainit sila. Ang mga computers natin, after they did work, mainit sila. Even our phones, diba? They heat up. Yung heat na yon, hindi yon ang mismong product na kailangang i-produce ng mga machines na yan, ng mga gadgets na yan. Pero they get that heat, that thermal energy keeps on getting produced as a waste product. It is an unwanted, an unintentional product of the conversion of, say, one form of energy to a different form of energy. And that actually means that for as long as lahat ng mga lahat ng mga machines, they always produce heat. I bet that you can still hear the dogs from our neighbor. Pero focus. For as long as you can see or you can feel thermal energy being produced by machines, as a machine is always doing that, it's kind of like it's a thing, we can say that no machine or no engine is still 100% efficient. This has been the 42nd edition of Physics 9, and what we were capable of accomplishing in this session. The first one is a discussion about the first law of thermodynamics. The second thing that we accomplished is a discussion about thermal efficiency. And then the last one that we were capable of accomplishing naman is a guided problem-solving activity on thermal efficiency. Yung ating mga learning competencies, marami sila, for this session are as follows. The first one is for you to be capable of constructing a model to demonstrate that heat can do work. So meron siyang discussion about that kanina. The second one is for you to be capable of inferring that heat transfer can be used to do work. And that work involves the release of heat. So itong release of heat na to, it is usually an unwanted and an unintentional occurrence. And then, the last part naman is, you're, I hope, capable of explaining why machines or engines are never 100% efficient. The contents of this session are found in the 7E-based self-learning module in Science 9. which I wrote. Particularly, you will find it in Unit 4, Book number 23, pages 11 to 13. This has been Sir CJ, and I hope that you learned something new in this session of Physics 9. I hope that you are having a great day so far, and that I hope as well that in the next edition, medyo mas quiet na yung mga dogs sa neighbors natin. Alright, so have a good day.